All right, so we want to start today with kind of sort of a review of what we were doing yesterday, but also just kind of integrating the other concepts that we were looking at last week as well. So the question here is, write the formula and the symbol for an ion with 16 protons and 18 electrons. So right away, we should be able to do a couple of things. With 16 protons, we know that that's our atomic number 16. We're talking about sulfur here. The other thing that we would want to look at is that we've got a unbalance. 16 protons, 18 electrons. Our charge is not balanced. So this is where we got away from what we were looking at in chapter 4, and now we're into looking at ions. Remember, protons are positive, electrons are negative. I have 2 extra negatives, so the charge here would be -2. So an easy way of, if you like formulas, we can think of charge as always being the protons minus the electrons. Another note here, writing the charge as -2 or as 2 negative, same thing. The order there doesn't matter. They convey the same idea. Olivia? It should. It should. To my knowledge, mastering doesn't have a preference on the order for charge. Preferences tend to be kind of individual based upon, how you might use that information. But for our purposes, it shouldn't matter either way. All right, let's take a look at another question here. We're looking at calcium and chlorine. Calcium is the element Ca, chlorine is the element Cl. We need to identify each as a metal or a nonmetal, and then answer some other questions about it. So for calcium, would we describe calcium as a metal or a nonmetal? Which part of the table is it on? It's on the metal side. Left side of the table, all metals. So calcium is a metal. How many valence electrons? Where is it? It's in group 2, so it has 2 valence electrons. How is it going to obtain an octet? Right, so this is what we were talking about yesterday. I need to look at the valence electrons, figure out how I'm getting to 8. I can either gain electrons to get to 8, or I can lose the electrons I have and work backwards to a noble gas that way. So the option is to gain 6 or lose 2. It's going to lose 2. We're always going to go in the direction that gives us what is the symbol and the name of it. Well, if I lose 2 electrons, I'm going to have 2 fewer electrons, which means I'm going to have 2 more pluses than minuses. It's going to be +2. The name of this is calcium ion. And so for positively charged ions, that's all that we really do. We just name the element and then attach ion to the end to tell us that it's an ion instead of the atom. And since we all understand what calcium is and where it is, we can all make the assumption that it's going to have 2 electrons, and it's going to lose those 2 electrons to form an ion. For chlorine, where is chlorine? Is it a metal or a non-metal? All right, it's tucked into that upper right-hand corner of the table. All of the non-metals are there. Excuse me. Okay, where is chlorine? What group is it in? How many valence electrons? So we find chlorine in group 17, group 7A. There are going to be 7 valence electrons. And so again, to get to an octet, we either gain 1 electron to get to 8, or we lose all 7 of these to go around the back. In this case, gaining 1 electron is going to be a lot easier. The result would be Cl minus, or Cl minus 1, or Cl 1 minus. All those would be considered okay. Here's a little bit of difference. When we go to name this, we're going to change the name of the substance slightly. With negatively charged ions, we are going to refer to them, we're going to change their endings to IDE. So chlorine becomes chloride, oxygen becomes oxide, bromine becomes bromide, sulfur becomes sulfide. The reason we do that is, again, to put a difference between a just plain old ion, which we assume is positive in charge, to an ion which we have designated as negatively charged. And so you will notice that when we get to other kinds of ions, the ions that are positively charged tend to all end with IUM, because they're either metals or they're derivatives that are going to give positive properties. The negatively charged ions are either going to end in IDE or are going to have some kind of a name change associated with them as well. Things like sulfate, carbonate, chlorite, those kinds of things, where we're not going to be able to recognize them as, hey, this is a substance on the periodic table. But by recognizing that ending, we're going to go, oh, this has to be negatively charged. So the majority of our topics for today are going to be about ionic compounds and ionic nomenclature, how to name compounds, and just kind of some things to recognize. So we talked about this yesterday. We kind of want to reiterate it here. What we have in ionic compounds are positive and negative charges. And those positive and negative charge, they attract each other. And that is what forms the bonds that create that substance. And so because of that, when we start looking at how is an ionic compound composed, what is it made out of? Well, we start looking at, well, what gives us positive charges and what gives us negative charges? So if I'm trying to look at the periodic table and predict what kind of compound would I have if I combined this element and this element, I can very quickly look at, well, what kinds of elements are they? If we've got a metal and a non-metal, well, we know metals make positive ions, non-metals make negative ions. A positive and a negative are going to attract each other. I'm going to get an ionic compound that way. But if I have two nonmetals, nonmetal makes a negative charge, nonmetal makes a negative charge, those negative charges aren't going to attract each other. In fact, they're going to do the opposite. They're going to repel each other. Ionic bonding is not going to be what draws together those ions. It's not going to be what draws together those nonmetals. It's going to have to be something else. It's going to have to be covalent bonding, which is what we're going to talk about on Thursday. And similarly, if I have metals, two metal samples, well, they both make positive ions. The positive ions would repel each other. So ionic bonding is not what holds a metal together. It's actually something else. It's called metallic bonding. And we're not going to get into the nitty-gritty of metallic bonding, but it basically explains why metals behave kind of the way that they do, why they have some of those properties we associate with metals, like malleability, like ductility, like conductivity. So in ionic compounds, we see that there are going to be positive and negative ions there. They are going to be drawn to each other through these attractive forces. Those attractive forces are called ionic bonds. Generally speaking, these compounds have high melting points and are solids at room temperature. And again, just for clarity here, when we're talking about positive and negative ions, what we're really talking about are metal ions and non-metal ions. Metal ions are the positive side, non-metal ions are the negative side. And the reason for these high melting points is because those attractions are very strong. Strong attractions tend to give us things that are going to be more clustered together, more ordered in their arrangement, more solid-like as a result. When it comes to chemical formulas for these ionic compounds, we have to understand what a chemical formula is. A chemical formula represents the ratio of one element to another element inside of a substance, inside of a compound. And those ratios are always going to be whole number ratios. We're never going to see fractions. We're never going to see decimals in a chemical formula. And that should make sense because ultimately we're talking about atoms here, and there's no such thing as a partial atom. I can't get 3/5 of a carbon atom. I can't get 2/9 of a nitrogen. It doesn't work like that. The important point that we need to make when it comes to ionic compounds and their formulas is that that chemical formula has to represent a balance of charge. Meaning that if I add up all of the positive charges in the compound, they need to equal the total number of negative charges in the compound as well. Now, this kind of naturally begs the question, if we know the charges, does that mean that certain groups of elements are going to be more likely to bond with other groups because of their similar charge? So will we see a likelihood of the group 1s reacting with the group 17s? And is that going to be more likely than the group 1s reacting with the group 16s? And the answer there is not really. charge balance tells us that the formula is going to be 1-to-1 if I have an alkali metal and a halogen reacting with each other, like sodium and chlorine here. But it is not limited to that. I can have sodium react with oxygen just as well. I can have sodium react with nitrogen just as well. The only difference, the only thing that we would notice is that the chemical formula would change accordingly. Since oxygen has a -2 charge and sodium has only a +1, I would need 2 of those sodiums to balance out the charge. The chemical formula there would be Na2O. And if I had nitrogen instead of oxygen, -3 charge for the nitrogen, 1 for the sodium, I would need 3 of those sodiums to balance out the charge of the nitrogen. All that would change is the formula itself. So here we have an example of magnesium. Magnesium is an alkaline earth metal, has a +2 charge. What we see is that that +2 charge means I'm going to need 2 chlorines instead of just 1 to get everything balanced out. Here we have an example with sodium and sulfur. Sulfur has a -2 charge, sodium has a +1. I need 2 sodiums to fully balance out the charge in the sulfur. Now, before we move on to this, I want to take a quick aside here and talk about Lewis dot diagrams. So those Lewis dot diagrams, what I'm referring to there, you can see in these pictures here how the sodium has this symbol with a dot around it, and the sulfur has a number of dots around it as well. Where does that all come from? Well, what Lewis dot diagrams are, these are visual representations of the valence electrons for a given element. In these, each valence electron is represented as a dot. When it comes to the diagram itself, we can think of that Lewis symbol, that elemental symbol, as having 4 zones around it. 1 on top, 1 on the bottom, 1 on either side. And so when we place these dots around that symbol, we need to fill those zones evenly. And so that's why if you look here at this diagram here, you can kind of see, okay, the magnesium has 2 dots. Why are those dots separated and not together? Well, that's what the rules kind of dictate to us. And so we can see that for chlorine, if it's 7 valence electrons, it has 7 dots. We can see that it's missing 1 more dot to get 8. Now, the whole purpose of this is twofold. First of all, we can use diagrams like these to help show where those electrons are going when ions form. So we can see that this magnesium is losing 2 electrons, and we knew it had 2 electrons to lose because the valence diagram showed it that. But we also can see this magnesium can only give 1 to chlorine. This chlorine already has 7. And if it had to add 2, that would get it to 9. That would overfill the energy level. So we talked about this yesterday. We can't overfill the energy level. If we got more than 8 in there, you'd have to start a new energy level to compensate.
So it won't always work like that then?
So yes, we're always going to see it's going to be an even distribution. It's going to cap at 8.
Right, but say that.
So if I had, which one had 3? Okay, so magnesium had 3. What I would see is that I would need a 3rd chlorine here to accept that extra 3rd electron. So when we're looking at these kinds of diagrams, that kind of gives us an insight into what has to happen to make the compound work. So if we go back again, what we can see again, so we've got these 4 zones here. We can very clearly see from this visualization what needs to happen to that element to get it to its full octet. And so let's just take a look at an example here. So if I'm looking at, let's pick on phosphorus. Phosphorus is in group 15, has 5 valence electrons. So I would put those 5 electrons, 1, 2, 3, 4, 5. Now, order of filling doesn't matter. What matters ultimately in the end is I'm going to have 1 pair of dots, and I'm going to have 3 unpaired dots. The location of them in relation to the top, bottom, left, right really doesn't matter. Well, because there's only 4 places that the electrons can go. So once I've filled all 4 areas, I have no choice but to double up one of the areas. Nope, doesn't matter where it's at. Again, this is just a visual tool to help us get an idea of what is going to happen to this element. And so from that standpoint, if we're looking at this ionically, we could gain 3 electrons. And if we gain 3 electrons, here are the 5 that we started with. 3 more, 1, 2, 3, would now give us 8 electrons around that phosphorus. It would also give us a -3 charge because we had to add those extra electrons to it. So that's how we get the phosphide ion. So if we're doing ionic stuff, we can see, hey, here's how many holes I have. Those holes are going to need to be filled by positive ions giving me electrons. Now, what we'll get to on Thursday, just a little bit of a sneak peek. The fact that phosphorus has 3 unpaired dots tells me that phosphorus is going to make 3 covalent bonds. Now, what those covalent bonds look like, well, that depends on what is reacting. But I know it's going to make 3 bonds because those unpaired dots are going to be what are shared between it and another atom to create a covalent bond to make a molecule instead of an ionic compound. All right, so let's go back. And now we can see, okay, this is what's happening here. I've got sulfur. Sulfur's got the 6 dots around it. It needs 2 more. Where do those 2 come from? Well, they're going to come from these 2 sodium ions because each sodium only has 1 electron to give. So I'm going to need 2 of them to give me the total number that I need. Now, visually, that's what's happening. And we could make those kinds of arguments. We could do the drawings and show that out. But there's another way that we can do it as well. Once we have kind of a handle on that, that is going to make a lot of sense as well. Here I have barium ion, Ba+2, and chloride ion, Cl-. Now I could draw these out and show that the barium is going to give 1 of these electrons to the chlorine. But the problem is the chlorine can only accept 1, and barium has 2 to give. So naturally, what's going to happen is the barium is going to go out and attract another chlorine to give the other electron 2. And we're going to get BaCl2 as a result of that marriage of these electrons moving around. Well, I want you to recognize one other thing, though. We can actually cheat this a little bit. And what I mean by that is if I look at the charge and I see that the charges are different, so +2 and -1, what I can do is I know that the relationship between those ions is going to be kind of a flipped relationship. I'm going to need however many ions on the negative side as there is charge on the positive side, and vice versa. We call this the crisscross method. In the crisscross method, all that you need to do, you're dating yourself. You know that, right? He's back there singing Jump. Yeah, there's only a couple of us here that know that one. I'm dating myself too, but I'm allowed to. I'm your professor. What you do, the crisscross method, you take the charges, you flop them, and they become the subscripts in the chemical formula. So the charge of 1 on the chlorine becomes the subscript on the barium. And since 1 is implied, we don't need to write it. The charge of 2 on the barium becomes the subscript of the chlorine. And so that's how we end up with barium chloride, BaCl2. So the Lewis dots give us the visual picture. This is what we think is happening inside of the compound. The crisscross method gives us a means of quickly identifying what the formula should be based upon the charges on the ions. So with that in mind, we can do problems like this, and we can do them relatively quickly. Because if I look at it, I see, okay, I've got sodium and oxide here. The charge on the sodium is 1. The charge on the oxide is 2. So I should be looking for Na2O, which is option number 2 here. The charge on the aluminum is 3. The charge on the chlorine is 1. So I should have 1 aluminum and 3 chloride. That'd be AlCl3. That's option number 1. I've got a charge of 2 on the magnesium, charge of 3 on the nitride. Crisscross those. I need 3 magnesiums and 2 nitrides, Mg3N2. That's option number 3. Okay. Now, what do I do if the charges are the same? What if it's a +2 and a -2? We don't cross them. Crisscross only applies if the charge, the value of the charge, not the sign, but the value is different. If they're the same, then it's going to match up perfectly 1 to 1. If I have 2 electrons from magnesium that are going to be added to 6 electrons on oxygen, 6 + 2 is 8. Oxygen's completely satisfied. Magnesium's lost all of its power. It's already balanced. I don't need to do anything further. So if the magnitude of the charge is the same, +1 - 1, +2 - 2, +3 - 3, we don't need to cross them. We just rewrite the formula 1 to 1. Magnesium oxide is MgO. Aluminum nitride is Al3, or excuse me, AlN.
Mg2 positive and N2 negative. Just be.
Correct. Yes. If the charges are the same, you just rewrite the 2 ions next to each other.
Even though they're positive and negative.
Right. Because if we're thinking about this from a transfer kind of standpoint, every electron that was needed to get rid of in the metal was accepted by the non-metal. There's nothing extra left over, and none of they don't need any more. All right. Other questions with this? Okay, so that's writing formulas, and so it's pretty easy if we know the identity, we know the formula of the ions, and we know their charges. It's easy to turn those into formulas because we either match them up or we crisscross them to figure out the chemical formula itself. Where this gets a little bit trickier is when we have to start working the other direction. We have to start putting words to these symbols. So the structure here is actually really simple. When we're naming, we always name in this order. Positive ion is first, the negative ion is last. That's always the order. Now, as we discussed earlier, when we have that negative ion, we are going to change the name of that negative ion to show that it is negative. That's where that IDE ending comes in. So it only applies to that top corner, that top right-hand corner of the periodic table. But all we're doing is we are changing the ending of that element to IDE. So again, oxygen becomes oxide. Sulfur becomes sulfide. Phosphorus becomes phosphide. We're changing just that last little bit of it. So that always is put on the end of that last word in the name. First word, rarely is it changed. Rarely is it modified. The only place where it is modified is if we're dealing with one of those metals in the middle of the table. And the reason for that is because we have to specify a charge on those. We can't just look at the periodic table and say, oh, that's +1. That's +3. So what you will see is that when we're working on this kind of information, you'll see a lot of tables like this, where we're trying to kind of break down the naming process for you into small steps and then have you combine those steps at the end. So thing like this, first column here is the name of the metal ion. And you can see that the names of all these metals are exactly what their element names are as well. So the metal ion, that's the easy part. Sean?
Okay, so
So when it comes to naming, notice that we don't really do anything with the charges themselves. None of these say, you know, potassium 1+ or iodine 1-. Oh, over here?
yeah. So I just noticed that every single one of them. Just trying to put the picture into.
Okay. Correct me if I'm wrong. Correct me if I'm wrong. I think I understand what you're trying to say. Let me see if I can put this into words for everybody else. So if I was given this formula, Al2O3, would I be able to work backwards to figure out the charges on the aluminum and the oxygen? And the answer is yes. All I would need to do is reverse that crisscrossing, and it would give me the charges that I was interested in. Now, that doesn't always work. So this is where understanding kind of positionally where things are on the periodic table help. You know, so for example, Ki, the fact that it's 1-to-1 just means that the two charges are the same value. Doesn't necessarily mean that it's +1 and -1. In this case, it is, but it could also mean that it's +2 - 2 or +3 - 3. You would have to go back to the periodic table and look at where is it, what kind of charge does it usually make to answer that question. But otherwise, yes. You know, if I'm looking at a compound that has a bunch of subscripts in it, I can reverse that crisscross, go back, and that would help me predict what the charge on the ions were.
So like what we're gonna do on the lower and stuff, we're gonna be given like the compound and then we gotta flip it and then name it.
You're gonna have to do all of this, yes.
Okay, and then whenever we're naming it, is it only the ending group that gets changed?
Yes, we'll talk about a little bit of a variance on that first word, but in a minute.
Okay.
For the most part, if there's a variance on the first word, it's because we're dealing with a metal in the middle of the table and we need to identify its charge because we have more than one.
And is it always the I?
So if it is a single element, like iodine, like bromine, like oxygen, it will be I. If it's multiple nonmetals making an ion, which we might get to talk about at the end of today, there are specific names for those. And what we will do is we'll give you a reference sheet that tells you what those clusters of elements are and what the names of those clusters are. All right. K2O. Let's name this thing. So, working backwards, we could use the periodic table and say, okay, potassium is in group 1A. It's going to be a +1. Oxygen's in group 6A. It's going to be a -2. We can also reverse that crisscross and get to the same results as well. Either way that we do it, we're going to end up with K, which is potassium, and O-2. O is oxygen, but we need to turn that into its ion name, which would be oxide. Put those two together, and we have potassium oxide. That's the name of our substance here. All right, let's do a couple more. Okay, here's an example in the first one where we can't reverse the crisscross to figure out the charges. Calcium is going to be +2. Oxygen is going to be -2. We know that based upon their position on the periodic table. The reason the formula is CaO instead of Ca2O2 is because, again, we've already got a balance of charge. We don't have to further complicate it. So Ca is calcium. O is oxygen. Change that to ide. So this would be oxide. This time we can reverse the crisscross, or we can use the periodic table. Aluminum 3 plus oxygen -2. We would have aluminum. Oxygen turns into oxide. So the compound here is aluminum oxide. The ions here for MgCl2 are magnesium +2 and chlorine -1. The name of the first part here is just magnesium. Chlorine, we're changing its ending as well. It's going to be chloride. So magnesium chloride is the name of this salt. So for these kinds of compounds, it's really just about identifying the correct elements, which is why we did all that stuff with the elements past couple of weeks. And then knowing to change the ending to the non-metallic part of the compound. All right, you've asked a number of questions so far. Are there any others that we want to address now? All right, here's another way that we can address kind of both concepts at the same time. We need to turn these into formulas and into names. So here's what I want you to do. Let's have you take about 3-4 minutes. At the very least, try to get all the formulas in. If you can try to put the names in as well, go ahead and do so. But at the end of, let's say, 4 minutes, we'll go through the answers. We'll kind of see, we'll do a little bit of a check and see how everybody's doing. All right, let's see how we did. All right, so a couple of things that might have tripped you up. If you're crisscrossing this one on the bottom right-hand corner, the aluminum nitride, that would have just been ALN. Again, you had +3 and -3. The charge is already matched. We didn't need to do anything more than just recognize that they would be 1-to-1. Aside from that, we also wanted to recognize we hadn't worked with some of these ions before. Remember, they all switch to IDE endings. So sulfide and nitride would have been the correct ions for the second and the third columns. All right, any questions with these? Okay, so now we're going to introduce a couple of concepts that are going to be, let's say, different. So this is having to do with the metal part, the first part of the name. And for that, we have to recognize that, compounds exist in the middle of the periodic table as well, not just in what we call the main group elements, those first 2 and last 6 columns. All those transition metals in the middle, they also make ionic compounds. And what makes them kind of different is the fact that they are capable of forming multiple kinds of charge. So with the exception of zinc and cadmium and silver, with the exception of those, which only form one kind of charge ever, every other transition metal has the ability to make multiple charges. And to signify the difference between one charge of that metal and another, we're going to use a Roman numeral to showcase what charge is being used in that compound. So that comes up in the name and in the charge as well. So if I have copper with a +2 charge, the name of that ion is copper-2. If I have copper with a 1+ charge, the name of that ion is copper-1. If I have chromium with a +6 charge, it's chromium-6. And so it's just this slight modification to the naming system that we would need to implement if one of these unique ones were present. And so your book goes into some details about, what some of these look like, what some of these are, and most of them fall into kind of a similar pattern. Most of them are either +2 or +3. There are a couple of exceptions in there. In particular interest and note here, I want to point out mercury, just because mercury kind of breaks the mold here. Every one of these has just a single atom with a charge. The mercury-1 ion is actually an ion pair. It's really interesting. what you have is you have two mercury atoms that are linked together. Each one of those mercury atoms has a positive 1 charge. Collectively, it has a positive 2 charge. But since we always evaluate charge on a per atom basis, that's why it's called mercury 1 instead of mercury 2. Because you've got two atoms sharing the 2 positive charge, one on each atom. So with that one exception, pretty much everything else there follows this rule about charge versus Roman numeral. And so all that we would have to do is modify accordingly how we name that first part of the compound. Alexis, did you have a question? Okay. Yes. Yeah, they all follow the same kind of pattern. Charge is Roman numeral. So what that allows us to do is when we get a problem like this, we have to recognize a couple of things. First of all, we have to recognize manganese, Mn, that's not in one of our common columns. It's a transition metal. How do I know what charge it is? Here's where we reverse that crisscross, and now we can figure it out. That fluoride being a 2 means that this has to be a positive 2 to this -1. My manganese is going to be manganese 2 because it's got a 2 positive charge. Fluorine turns into fluoride. The name of the compound is manganese 2 fluoride. That's the only modification that we have to make. We have to identify the charge on the manganese because it could have more than one. But the Roman numeral is the charge. How did I figure out that charge? Well, again, that's where we think about reversing that crisscross, turning those subscripts up to figure out charges. We can also go off of the periodic table as well. We know that fluorine's -1 and there are 2 of them. So if I've got -2 on one side, I have to have +2 on the other. So with that now, we have a more complete set of charges as far as the periodic table is concerned. We can pretty accurately predict most charges based upon these kinds of positions. And in the middle here, there's not really a hard and fast rule for figuring out what charges we would expect, but we can use our context from the chemical formula to figure out what charge is there if we didn't know. All right, let's take a look at another example. FeCl2. Well, Fe, we know that is iron. And we know Cl, that's chlorine. So that's going to be chloride. So iron chloride sounds like a really good start, but it's incomplete because iron is a transition metal. Iron has multiple charges possible. So how do I know which iron we're talking about? I have to figure out the charges. And so again, I can use context. I can look at this and say, okay, chlorine is -1. There are 2 of them. So I've got 2 negative. It must be 2 positive. Or we can reverse that crisscross again and know that this is a +2 iron, which would make this iron 2 chloride. Again, the charge is the Roman numeral. All right, try this one yourselves here. We've got a compound of manganese. Let's take 1 minute. What is the name of this manganese compound? All right, this one is a little bit more tricky than it seems. What we have to recognize is that our reverse crisscross here is actually going to put us in a little bit of trouble. Oxygen's a -2. We know that off of the formula. We know off of where it is on the periodic table. So if I have 2 of those -2s, that's -4, which means that the manganese has to be a +4. So the name of this compound is manganese 4 oxide. Now, the question you might be asking is, well, how did we get MnO2 then? Well, it's kind of the same thing that, and we see this a little bit with these transition metal ones because, 1, 2s, and 3s don't always, work out evenly with 3s and 4s. With Mn+4 and O -2, I only need 2 oxygens for the manganese to get rid of all that it has. If I do the crisscross, I'd get Mn2O4, which would reduce to MnO2. Generally speaking, chemical formulas are always presented in kind of like the lowest reduced fraction kind of form. And this is kind of the reason why. So, like I said, reversing the crisscross, it works most of the time. There are a couple of places where we could get into a little bit of trouble with it. This happens to be one of those places. All right, let's look at another. Yeah, we've already done that. Now let's reverse it. If I have the name of the compound, can I flip it around and give us the formula? Well, nothing really has changed here. In fact, it's been made a little bit easier for us. Since I have the Roman numeral, I don't have to look to the periodic table to figure out its charge. I already know. Iron 3 is Fe+3. Chloride, well, I know that's chlorine. And chlorine's in group 7A, so it's going to have a -1 charge. Charges are different. I can crisscross. FeCl3 is the result. All right, quickly on your own here. Work on these last 3 yourselves. keep in mind zinc. Zinc is one of the ones that does not change. It does not have a second form. It's always +2. All right, go ahead and check your answers here. So probably the tougher thing is, yeah, you had to go find all the stuff on the periodic table again. So you had to go back to what column is it in, what charge is it going to carry. Once you did that, part A, the charges were the same. 2 for the nickel, 2 for the sulfur. So they evened out 1-to-1, nickel sulfide, NiS. Chloride's a -1. I told you that zinc was a +2. So crisscross those, we get zinc chloride, ZnCl2. Iron 3 oxide, iron is a 3+, oxygen's a -2. Crisscross those, Fe2O3 is the result. All right, so we have effectively carried the first 3 sections here in the chapter. Section 4 is something that we're doing more of the same. We're just adding just that little bit extra in terms of difficulty. So what I'm going to do is this. We've got about 4 minutes. I'm going to talk about it a little bit. I'm going to push the homework assignment to Thursday night. So try to do as much of it as you can. If you get stuck on this polyatomic ion stuff, just wait it out. We'll talk about it at the beginning of Thursday, give you a little bit more time to work on it from there. Hopefully from there, we can kind of figure out the rest. But the assignment, I will tell you, the assignment is on the longer side because we've got so much of that naming stuff in there. But all that we're adding to this are the idea of polyatomic ions. These are those atom clusters that I was talking about, where you've got non-metallic elements that are banding together to form some kind of a molecule, but that molecule happens to have a charge on it as well. And that charge is almost always negative in value. There's one exception. The one exception is ammonium ion, NH4+. But even that follows kind of our traditional value in terms of it ends in IUN, just like every other metal ion ends in IUN as well. Majority of these are negatively charged. And this is the list of kind of the most common polyatomic ions out there. Now, don't worry about this list in terms of trying to memorize all this stuff. You don't need to. When it comes to naming, you're going to be given this list. It's more about, can you recognize the clusters and choose the correct cluster when we encounter it. So if you see ClO3, instead of trying to beat your head against the wall, figuring out what that is, you look to the chart and you say, oh, ClO3, that's chlorine. From there, the structure is exactly the same. We name the metal. We name the non-metal, or in this case, the polyatomic ion. And we put the two names together. That's the name of the compound. And as far as charges are concerned, yes, there are a variety of mixed charges up there. But when it comes to handling the formulas, we do the exact same thing. It's a matter of charge balance. So that means that we can crisscross them if they're different. We can match them up if they are the same. It falls into a very familiar pattern. The only other thing that we might see that is different is the use of parentheses. Because we are dealing with clusters of atoms now instead of just individual elements, we use parentheses to kind of help designate that we have a polyatomic cluster as opposed to individual nitrogens or individual oxygens. So if I'm looking at nitrate there, nitrate is that NO3 cluster there. That whole thing stays together. And so if I need multiple of them to make charges balance, I put them in parentheses to show that the whole cluster is being doubled. The whole cluster is being tripled, whatever the case may be. So we'll leave today with just one example, just to kind of show what you're doing here. If it's enough to springboard you into the homework, great. If not, we'll do some more examples on Thursday before we talk about molecular compounds. Aluminum bicarbonate. So for aluminum, we can look at the periodic table. It's in group 3A. We know it's +3. For bicarbonate, we need to look at a list here. And we can see that bicarbonate is this cluster on the list, HCO3 -1. They are listed as bicarbonate. If you see the prefix bi, it's an old school way of saying hydrogen. Bicarbonate is hydrogen carbonate. Bisulfate is hydrogen sulfate, and so on. So the cluster is HCO3 -. I can see that I have a mismatch here, so I'm going to need a crisscross. I'm going to have 1 aluminum. I'm going to have 3 bicarbonates. So if I did it this way, it would look a little bit confusing. I'd be seeing, okay, HCO3 or HCO33. Not sure. By putting the parentheses around it, that tells me, that tells everyone watching that there are 3 of these bicarbonate clusters to balance out the charge of the aluminum. Now, when we say that verbally, most common way to kind of contextualize that is we would say AlHCO3 taken 3 times. So that taken 3 times tells me that I've got 3 of those HCO3s. Okay, so that's where I'm going to leave you for today. And we'll pick up with this, more of this on Thursday. We'll also get into molecular compounds as well. Have fun in lab.